Swayam Prabha. Digital India. Educated India.
Welcome to this session on rapid prototyping under the course Advanced Manufacturing Processes. In the last session, we have discussed about few rapid prototyping processes, basics of rapid prototyping, its features, major processes in rapid prototyping technology and their applications. In this session, we will be discussing and studying few other processes in rapid prototyping technology. They are basically thermojet processes, ballistic parts manufacturing and rapid manufacturing, in short RM process. We have already discussed that rapid prototyping technology is the fallout of customers' demand for speedy delivery of the products. This is not only from the customer side, but also the speedy delivery of different inputs to the subsequent stages in manufacturing shops also triggered the development of these processes. So, these are some of the technologies that could compress the time in manufacturing. In other words, we can say that the manufacturing lead time could be compressed, and accordingly the product could be delivered either to the customer in the field or to the subsequent stages in the manufacturing at a rapid pace. But there are different issues and different techniques involved how to go about it. In the last session, we have already discussed there are a number of techniques that can be employed for producing parts under this category of manufacturing, that is rapid prototyping technologies. We have already studied laser sintering process, we have already studied laminated object manufacturing processes and so on, and each process is slightly different from the other as far as the working is concerned, but basically all the processes are following the same principle to the extent that these products or the parts are produced layer by layer, putting one layer on top of the another through different techniques, and these are directly being produced from the CAD model, then transforming this model into some other formats and thereby directly getting the 3D part in the machine that is connected to the CAD terminal. So, in the other processes like laminated object manufacturing processes, that also we have seen As we have already discussed in one of the previous sessions, that laser plays an important role in these processes. Say for example, in one of the processes we have discussed, if there is a sheet like this, then laser can be applied to specifically carve out one object from this, which is dictated by the CAD drawing in the CAD terminal. So, this can be worked out in the CAD terminal here. And this can be directly connected to the machine, RP machine. So, this is the output of the CAD terminal, this is the CAD terminal, and this can be given to the RP machine as the output of this CAD terminal, and for this RP machine this will be input information, and this will work on this input information, and the final part will be built up in this machine depending on different principle as per the working of the mechanisms. Now, let us look into another process in this series. This is called thermojet process. Let us discuss this thermojet process first. This process is particularly useful for investment casting process. As I have already indicated, this rapid prototyping products are at many a times intermediate input to some other processes in the manufacturing shop. Say for example, in casting we need a pattern. This pattern can be produced very effectively and very economically by different rapid prototyping techniques. This is one of the processes like thermojet process, which could be very useful in investment casting process. Wax parts are produced using this system can be used as sacrificial patterns for investment casting. As all of us know the basics of investment casting, where the pattern is to be invested or sacrificed. Therefore, this wax or materials of the type whose melting point is much lower, with less heat it can get melted, can be used as a pattern material in these type of processes. And on the other hand, these type of materials, low melting point materials like wax etc., are very good to be used in the RP processes. The main advantage is in the production of relatively complex castings without the need for tooling. Cost effective complex metal parts may be produced from CAD models in a relatively short period of time. This is I have indicated at the beginning of this session. Even CAD terminals can be used to produce the model very effectively within a very short time. Moreover, parts modification can be very rapid with the use of CAD terminals, in a way that already there may be CAD designs or CAD models available for a part which may be to some extent similar to the present part is needed. Therefore, instead of starting from the scratch of the new part, we can take the help of the basic model available in the CAD database, and then we can go on modifying the existing model to get the new model, and this model subsequently can be converted or transmitted into other formats for subsequent processes of or steps of manufacturing. Generally, wax patterns need to be finished to a very high standard. One problem with the system is the support system used, which leaves undulations on all downward facing surfaces of the pattern. The supports have to be removed and surfaces cleaned by hand. This process is best suited to small numbers of complex parts that would otherwise require a significant amount of coding to accommodate undercut features. The schematic of this process is shown in the figure. The process is shown in the screen, the basic scheme of the thermojet process. Here this is the platform and this is the object being manufactured. And as I have indicated at the very beginning, this is a layer by layer manufacturing process in most of the cases. So, therefore, the material is getting deposited on this product and this platform will be lowered in a step, so that next layer can be deposited on top of this. So, if once this layer is being produced, then this is lowered by a thickness equivalent to the next layer to be produced, and therefore, the subsequent layer or the next layer will be deposited like this on top of this. And this xy movement of this or the movement of this head, we can think of this as like a printing head, as in the case of inkjet printers, where inks are being deposited on top of the paper, which of course we see in the form of 2D. But in this case, since every time one layer is being produced, which is 2D in nature obviously, then the platform will be lowered by that distance and one more layer will be produced. So, with subsequent deposition like this will form a 3D object as shown in this figure. So, we can here control the movement of the platform as well as the head either way. Nowadays, there are excellent facilities like computer numerical facilities are there, which can be integrated to any of the RP machines for controlling the x, y and z movements of the either the platform or for the printing or the deposition head. Now, let us move on to another process, that is ballistic particle manufacturing process, in short known as the BPM process. The ballistic particle manufacturing system uses piezo driven inkjet mechanism to shoot droplets of molten materials which get cold welded together on a previously deposited layer. A layer is created by moving the droplet nozzles in x and y directions. So, this is in a sense a 3D printing concept. After a layer is formed, the base plate is lowered by a specified distance and a new layer is created on the top of the previous one. Finally, the model is created. Then the rapid manufacturing process, RM process. So, this can be considered as an extension of rapid prototyping technology. It involves automated production of parts by instructions directly fed by the CAD data which is modeled earlier. It is believed that the process of rapid manufacturing or the RM process will develop into a compelling market in future and will cater to customized requirements worldwide. Currently, only a few final products are prepared by these machines. As the technology and demand increases, the product range will also increase, it is expected. This technology is currently not suitable for mass production. It needs further development or further adaptation to make it more suitable for mass production environment. And unless the process is economical, it will be hard to push for the industries to adopt this process. It is mainly suitable for small batches and one off production articles. It is relatively cheaper since no tooling are involved. Some of the final components produced are as follows: customized dinner wear, customized helmets, jewelry patterns, electrodes for spark erosion, reverse engineering parts, etc. Now, let us see some common applications of rapid prototyping technologies. As I have already indicated, they are very useful in product design and development, in reverse engineering, prototyping and concept modeling for market research, then short production runs, rapid tooling, models for stress analysis, industrial design and architectural modeling, jewelry design, in medical applications, crafts and fine arts. Some product examples of rapid manufacturing can be listed like this: parts of small table fans, containers for micro oven and projectors, body of scooters, refrigerators, washing machines, mobiles, etc. These are some of the products that can be produced. Some parts of this can be produced very effectively and economically by applying this rapid prototyping technologies. Some other applications of rapid prototyping include: it has been used to build the world's smallest robots using the stereolithography technique. In the previous session, we have discussed about stereolithography technique. In medical applications, rapid prototyping technology is used to make exact models resembling the actual parts of a person through computer scan data. This is one of the significant applications of rapid prototyping technologies. Nowadays, the medical sciences, the advancement in medical sciences have given us the opportunity to scan through almost all the body parts. Of course, this we can say is a wedding of medical sciences and engineering, which has given rise to some of the techniques and the equipment that can be used to scan each and every parts of the body with minutest details. Say for example, if I need to scan this limb of my hand, this can be done by using some imaging equipment. And the subsequent development in the processing of images has given rise to the technique that the images can be again reproduced or put together to form a virtual model of the bone of this that is exactly similar to that of inside my hand. Therefore, by using this imaging and then processing this image, we can reproduce on our CAD screen a virtual image of the bone that is inside my body. Now, for doing some tests which the doctors cannot in a live situation on my hand owing to different problems can be carried out on a model of the exact model of the bone that is existing in my hand, which is the virtual model of which is already being produced in the CAD model thanks to the technology of imaging. Now, we can rather have an exact replica of the bones or the virtual image that is stored in my computer or the CAD terminal by using rapid prototyping technology in the form of a 3D model, which can be got printed or produced as part of a rapid prototyping part, which is nothing but the exact replica of the bone which I am having. Now, the doctors has the flexibility, they have the flexibility to work upon, to examine different aspects related to this, which will reduce my pains or my discomfort if it would have been done or carried out in my body. So, this is one of the very significant advantages or applications of rapid prototyping technology. These models can be further used to perform some dummy trials or even the trial surgeries before the patient's actual surgery. This is what I have already indicated. Different tests can be carried out, different surgery, dummy surgery can be carried out, whether it is feasible or not, whether it can be successful or not, which is not possible. That experimentation, whether it will be successful or not, cannot be carried out in a living human being, or this is not ethical as well, but which is possible now. This is possible with the help of these technologies. Rapid prototyping techniques are used to make custom fit masks that reduce scarring on burn victims. The process is made by digitizing the patient using non-contact optical scanning. This is another very significant applications as far as the human life is concerned, human comfort is concerned, or advances in human treatment is concerned. We can reduce the sufferings of a patient by using these technologies, which is very significant. The scan data is used to produce the RP model of a mask that fits perfectly to the patient's face. Then the selective laser sintering SLS can be used to produce superior sockets, knees, etc. This we have already discussed the SLS technique in the previous session. The clinical results indicate greater comfort, fitment and ease in such patients. Such design features are feasible through rapid prototyping technologies. Very tiny miniature parts are made by electrochemical fabrication, which also comes under rapid prototyping technology. In the electrochemical fabrication, the electro deposition of nickel layer by layer is done using a rapid prototyping masking technique. In this electrochemical masking technique, it is easily possible to produce very small working mechanisms. Let us discuss another application of this process. This is vacuum casting. Vacuum casting system is used for casting polyurethane parts using silicon rubber molds. Vacuum casting, which is also known as silicon molding, is a very common process in the rapid prototyping industry. It is normally used in the production of small series of functional plastic prototypes. A broad range of liquid thermoset plastics, that is nothing but polyurethane resins, are available for casting these parts. Polyurethanes with different physical properties enable the production of prototypes which are used for functional testing under different conditions. In order to make these components more aesthetically attractive and providing variety, pigments are added to polyurethane resin for producing parts in different colors also. Now, let us note few developments in the rapid prototyping technologies, the directions, new directions, etc. In stereolithography, 3D Systems have launched its largest SLA machine. 3D Systems is a company which is very premier in rapid prototyping technologies. So, they have introduced one of the largest SLA machines. SOMOS is a thermoplastic elastomer that allows SLS to now make flexible rubber like parts. These are some of the advancements in this field. Cast form PS can be used for making patterns for investment castings. Stratasys unveiled a new FDM maximum machine, that is fused deposition modeling machine, which operates 50% faster than previous FDM systems, which is quite impressive. It also offers one of the largest build envelopes in the RP industry. The new FDM maximum machine accommodates either very large parts or numerous smaller parts. It uses two extrusion heads, one for building the model and the second for depositing the support material. With the introduction of Z42C 3D color printer, Z Corporation became the first RP equipment supplier to offer a device that makes parts in multiple colors without any secondary operations. This is a significant step, as we have already discussed in the previous session, that sometimes secondary operations, mostly the finishing operations, may be required following the rapid prototyping production of any part, depending on the requirements at the application end. This is because it leaves some of the step-like structures at the outer edges or the outer periphery of the outer surface of the part as it goes on building up the layers. However, if this can be eliminated, then the cost of the operation of the secondary processing as well as the time involved in the secondary processing can be eliminated, thus making the entire process more productive. Color is applied to the surface of the parts to a uniform depth of about 0.08 inch in this type of systems. A typical small part can be printed in 1 to 2 hours in monochrome or 3 to 6 hours in full color. Now, let us see few future developments in these technologies. As the rapid prototyping technology gets further advanced, with better and new techniques becoming feasible and practical, it can lead to substantial reduction in built up time for manufacturing. This will make rapid manufacturing economical for wider variety of products. Further improvement in laser optics and motor control can improve the accuracy, as currently the accuracy is largely limited in the Z direction or the vertical direction. Z direction is generally considered as the vertical direction, x and y, and this is considered as the Z direction. The accuracy of other two planes x and y can also be increased further with the improvements in the CNC technology or with the improvement in the motor control system, because as we know the motors are responsible for giving the motion to the table or the printing head or the laser head, because the movement of the either the laser head or the movement of the table, this table x y movement or the z movement, as we have been talking about, each time one layer is completed, it is lowered by a distance. Now, if this x, y and Z, these movements can be fine tuned. Say for example, now the minimum distance moved can be achieved is say 0.1 micron. If it can be reduced to 0.01 micron, then the accuracy of producing these parts will enhance. This can be explained like this. Say for example, this is the parts to be produced. Now, this part will be produced in the rapid prototyping concept like this. First one layer will be produced. On top of this, so this layer, first layer is being produced. This is say first. On top of this, the next layer can be produced. So, next layer will be produced say like this. Next layer will be produced like this. Next will be produced on top of this like this. So, ultimately, so this will be the profile of producing the part. So, this is what the layer by layer producing. Now, here as we can see, these edges or this surface is nothing but it is something like step like structure. If we see this part on a magnified scale, it is something like this, and this is because we have produced one layer in this step, or we can say this is nothing but one step, and correspondingly this is the Z movement. Now, my point is that if this Z movement we can bring it down to this, say for example, so this will be say Z by 2. Therefore, then this step height will also be reduced to something like this. So, this will result in a step height something like this, and this is a much finer surface than this surface finish, which is poorer than this is say R A 1 and this is say R A 2, this is poorer than R A 1. Now, this Z by 2 we can achieve only by the mechanism or the designing of still finer motors or other mechanisms responsible for lowering this device. So, is the case with the other control of x and y directions as well. In those directions also the motor control plays a vital role as far as this accuracy is concerned. So, this is a case of accuracy as far as the surface finish is concerned. The development of new materials and polymers which are under the process of development by the rapid prototyping companies are less prone to curing and temperature induced warpages. Much anticipated development is the introduction of non polymeric materials including metals, ceramics, composites and powder metallurgy. This is another significant development. When first rapid prototyping technologies were developed and the techniques were put into use, then it was found that mostly the low melting point materials are suitable for these processes. Therefore, like polymer based, mostly the polymer based materials were used for making the patterns, etc., or simple parts. But in the industries, as we know, most of the parts are made from some engineering materials like metal based materials, alloys, ceramics, etc. Therefore, as the technology got improved, when it was found that the metal powders or the ceramic powders could also be used in these machines, it was considered to be a big breakthrough or a significant development in these technologies. If this is achieved, then more tough and strong materials can be used to produce components to give better mechanical and general properties and provide good service. Developments in ceramic composites can further increase the range of rapid prototyping. Currently, the size is also a restriction. Further developments in this direction is also expected in the near future. Mostly this process is suitable for small parts, like we have discussed the parts that are being produced in some of the forming processes, which are huge in dimension. These are generally not possible as because of the limitation of the machine, operation of the machine. So, if some more advancements with some researches in this direction, we can produce or we can come up with some such huge giant machines, then probably huge parts can also be produced. Currently, the demand of these products manufactured by RP Technologies is low, but with further advancement in technology, further awareness level and training, the demand will certainly be increased. It is expected. Due to lower demands, the utilization level of such equipment is also low and is in the range of around 50 to 60%, which is industrially not very encouraging. Advancement in computing systems and viability to support net designs from a distant country to be fed directly on the RP machines for manufacturing can be a new possibility. The engineer or the product designer can sit in one country and can operate or produce the part where exactly it is needed, which may be in another country. Let us talk about the RP scenario in India. As I have already indicated, overall awareness level regarding this technology is not very high, and so is the case in India. Therefore, the potential users are unable to determine how the advanced technology can help. In view of high equipment cost, very few organizations can invest in the new machines. That is how the use of application of rapid prototyping technology as far as India is concerned is still very limited. Now, very quickly let us note a few limitations and challenges as far as the rapid prototyping technology is concerned. Currently, rapid prototyping technology is more limited to modeling and making of specimens and designs. Rapid prototyping machines are very costly. Number 3, the technology is currently limited to making of paper and plastic type of products. It is yet to go towards the metals, alloys and ceramics in a big way. Replacing steel by composites is still not easy and people fear its implications. If this becomes a reality for non-strength requiring applications and non-structural applications, then RPT will grow in this area as well. It requires sound knowledge and expertise of CAM and modeling software. This technology is, we can say, is based on the modeling knowledge and of course, the CAM knowledge also. New materials are being experimented and used, and with its outcome further growth is expected in near future. Manufacturing of tools, products by composite materials through RPT is a challenging field in the manufacturing area. This can become a reality in near future. Rapid prototyping is not immune to the wide ranging obstacles that limit the growth of new products and technology. The vast majority of people and companies prefer technology and applications that are fully developed and which are mature in nature. However, rapid prototyping technology as it is considered now is yet to mature. In other words, people do not want to take any risk. This is another challenge. Unless we go ahead with adopting the technology, bravely experiment it out with the new developments, even the developments do not get triggered. Computer based modeling and prototyping is another challenging task here. It needs high speed computing facilities and high skills in modeling. Then the cost related challenge is, the common misconception is that RP is an expensive technology. In some typical situations this could be true, but if the articles are one off and the facilities are far off. Exceptionally, there are ample applications where RP is a less expensive solution when the time and output quantity is considered. Another important factor is the resistance to change. This is a common perception as people live in the past and avoid change. Difficult to give away old habits, routine practices and lack of adoption. That is how RP is also facing a resistance from the traditional goers or tradition lovers. People feel it safe to develop products in the traditional manner which they have been doing for years. People feel it risky to use new and unproven technologies. RP companies being fewer in number limit the marketing efforts and industry awareness. Most of the engineering and manufacturing professionals are not fully aware of RP power and its implications. This is also another factor that needs to be sorted out for full-fledged applications or adoption of RP technologies. Now, let us summarize what we have discussed in this session. In this session particularly we have focused on rapid prototyping applications, few variants of rapid prototyping technologies like rapid manufacturing technology, then the limitations and challenges of this rapid prototyping technologies and the new developments in these technologies. We hope this session was informative and interesting. Thank you.